All right, good morning, everybody. Can you all hear me?
Yeah, I can hear you.
You can hear me, okay. Can you see the board okay? Is it blurry?
Yeah.
Okay. So, just some announcements. So your chapter 25 homework is due on the 6th. Your second exam is on Friday. It's an in-person exam, so I'm expecting everybody to be here during your lab meeting. And so I will give you your exam during your lab meeting, and we'll follow the same protocols as we did last time regarding you have to show me that you're clear to be in the building. Okay. Anybody have any questions regarding that? The exam on Friday? To study for the exam, I sent you a link with the department's old website, and I have really all the sample tests for in-person, all the sample in-person tests there. Okay, those are good examples. This is one of the first exams I gave for this class. It also has a lot of resources, so you can check out that site. Okay. Also, besides studying the sample exam, by the way, there's also a sample online exam on Canvas. You can play around with that too. There is a set of conceptual questions with answers on Canvas. You can use those to help study for the exam if I think they're beneficial to you. Study the homework problems. Make sure you go over the techniques that you've used to solve the problems, because really that's what I look for. Do you understand the concepts and the techniques that you applied in solving the problems? And then go over the in-class problems we did. Okay. Again, it's going to be some multiple choice, some short answer, multiple choice for the first part of the exam, and then the rest is problems. Now I do this second exam differently because I know this unit's a little bit harder. You will have to do four problems on the exam, but I'll put like 5 or 6 of them on the exam, and you will choose to do 4 of them. And you have to tell me which ones you want graded. I'm not going to grade the best 4. That takes too long. Okay? If you don't tell me which ones you want graded, I will grade the first 4. I hope everybody's clear on that. Okay. I was happy to see people on Discord setting up meetings so that you can work on worksheets and stuff. I like that. That's the best way to learn physics is to work together and discuss course materials. And I highly encourage you as a class to do that. Set up meetings to study for the exam or work on homework. Okay, I highly encourage that. So I was very happy to see that. I think there was somebody set up a party to help work work on the worksheet. Okay, that's good. You can do this for the next assignment too. I think it's very helpful that you do that, because then you get to see the discussion of concepts from another person's perspective, not just me. You can also watch YouTube videos. Okay. Questions? All right, maybe we'll have questions on Wednesday regarding the exam. But remember, we are meeting in person. And since we are meeting in person, there will be open lab times before our 9:30 class, after the 11 o'clock class, and after the 3:30 class, the 2 o'clock class. Okay. The open lab times are listed on Canvas. Please check them if you're interested in asking me questions about the Ohm's Law lab that you're going to be working on. Okay, don't wait till the last minute. And I will be giving you multimeters if you haven't picked them up yet. I had 3 people come up the other day on Friday, and I gave them multimeters. So you guys need a second multimeter to do this lab. What I want to do today is finish off this, giving you techniques to calculate the electric potential. I'll say a little bit about applications. And I have this out of order. I want to do one special example, and then I'll introduce you to the next unit, which is on capacitance. Okay? So last time, we spent quite a bit of time calculating the electrical potential of a system of charges, or a continuous system of charges, based on that equation, which is based on the electric potential due to a point charge. This method is not always applicable, especially if you have a very, very large charge distribution. So if you want to calculate the electrical potential for a very large charge distribution, like a line of charge, then we go back to our definition of delta V, and calculate the electrical potential difference between 2 points. And if we know the electrical potential at one point, then we can find the value of the electrical potential at some other point in space. Regarding a question in the chat on our multimeter, if you want to come Tuesday or Thursday to pick up the multimeter, I'll probably be here tomorrow, but I have a 3-hour lecture. But email Tyler, okay, Matt. Let him know you're coming, or let you know you want to come Tuesday or Thursday, and then see if he's available. Okay? I won't be here on Thursday. All right. So this allows us to find the electrical potential between 2 points. And if I know the value of V at A, then I know the value of V at B. So if I want to find V as a function of R, I would integrate from some point in which I know the electrical potential to some arbitrary point in space. If I know V here, then I got V sub R. And so I'm going to do a couple of examples showing you how we do this calculation. Okay? So let's go to our first example. We want to calculate the electrical potential for a uniformly charged insulating sphere of radius r. And we're going to integrate the electric field over a chosen path. So let me draw a picture of my sphere, a uniformly charged sphere. And it has radius r, total charge q. Okay. How we integrate doesn't matter, but you want to choose the easiest way to do this. So I'm going to use this expression to calculate the electrical potential outside of this and inside of this. The E that we use in this expression is the electric field that's defined in that region of space. So the electric field out here is different than the electric field in here. So basically I have to do two integrals, one for outside and one for inside, because the E is defined differently outside the sphere than inside the sphere. We know that. Okay, we know that for outside the sphere, that's the electric field. And I'm not going to spend time deriving this. I'm going to assume you know it because we've done a problem similar to this. Inside the sphere, the electric field looks like this. You can prove it to yourself using Gauss's law. Okay. But I don't want to spend time deriving this again. We did a problem at the end of chapter 24 where actually kind of I went over this. Okay, so I want to find the electric field outside first, and then I'm just going to move inward. And the reason why I want to do that is because I know this thing is finite in size. I know that I can define V to be 0 at infinity. So I'm going to start out at the outside and move inward. And so I'm going to integrate the electric field from infinity to R. And this dot product is easy. It's just going to end up being KQ over R squared dr. Now, what's my problem again with this thing?
It's backwards, the bounds of integration.
I have too many R's there, right? It's confusing. So can I put primes here then?
Oh, that.
And really, I'm deriving the electric potential due to a point charge right here. So V sub R minus V at infinity is equal to, what does this integral give me? It's going to give me KQ over R from infinity to R. And so V sub R, because we know that's 0, so V sub R is equal to K Q over R for R greater than or equal to R, big R, sorry. Now what we want to do is find the value inside. One of the important things to understand about the electric potential as you go from outside to inside, the electric potential has to be continuous over the boundary. The electric field is the derivative of electric potential, and the only way you can take the derivative is if the function is continuous. Furthermore, if the function for the electric potential is not continuous, the electric field then has no physical meaning. So electric potential has to be continuous over any boundary. Electric field does not. If the electric field is not continuous over a boundary, it just means you have a charge on the surface. Okay, and we've talked about that. That's important to remember. Okay. All right, so we want to use this again. We want to integrate from the outside in. I'm sorry, from somewhere inside to another place inside.
Professor, I have a question.
Yeah.
Did the negative in front of the integral, did that disappear when you integrated it?
Yeah, because when you integrate this, you get a minus sign, and then you have another minus sign here that becomes a positive.
Gotcha, thank you.
Okay. So we want to integrate this equation because this is the equation for the electric field that is valid inside here. But what am I going to choose as my bounds? Well, obviously this is one of them. What's my other one? What's my other bound? Well, I have to choose this point so that I know its value. Where do I know the electric potential inside the sphere? Well, I know it on the surface of the sphere because I know that the electric potential has to be continuous over the surface of the sphere. So I have to evaluate it from the surface of the sphere to some point inside the sphere. So I'm always going from some place where I know V to some place, some generic place V sub r. And there's a minus sign there. This time when I integrate, the minus sign is not going to disappear. Okay, because I have a r in the numerator. So when I integrate this, I'm going to get k q over r cubed r squared over 2 minus big R squared over 2. But V sub r is the electric potential on the surface of the sphere. V sub big R, sorry. So then V sub little r is that. And we can collect terms and rearrange this because you have a plus kq over r here and a plus kq over r here. We can arrange terms, and I'll let you check the algebra. I'm just going to state the answer. You get the following expression. Okay, and so V sub r is k q over 2 big R times 3 minus r squared over big R squared. So let's take a look at this. When you're on the surface of the sphere, this ratio is 1. 3 minus 1 is 2. The 2's cancel, and I get the electric potential on the surface, which is continuous. You can see that it's continuous. When you're at the center of the sphere, when r is 0, you get 1.5 times kq over r. So the electric potential, and it's negative. I forgot the minus sign. The magnitude of the electric potential here is 1.5 times the electric potential here on the surface. Or another way to say it is that the electrical potential on the surface, the magnitude, is 2/3 of that at the center. Questions on that? Okay. Let me make this graph bigger. This is a graph of the electric potential on the surface, electric potential inside and outside the sphere. At the surface of the sphere, it is 2/3 that at the center. If you call V naught the electric potential at the center, then the electric potential on this surface is 2/3 V naught. So inside, the electric potential goes as negative R squared. It's quadratic. Outside, it goes as 1 over R. All right, let's do another example. This one is with an infinitely large charge distribution. So for sure, I cannot use the kq over r expression. And remember the answer to this question because I'm going to use this answer in an example I'm going to do in the next chapter. In fact, I can almost do it now. Okay? So let me go through this one. So suppose we have two concentric cylinders. Okay, they're shells. Because of their symmetry, you can almost treat them like line charges. Okay. And you calculated the electric field for one of these systems in chapter 24. So I'm going to draw this using two different views. In fact, this problem is important if you're somebody who works in electronics, who's working with very small electrical signals. So let me draw the inner conductor. And it'll draw the outer conductor in purple. These are infinitely long. Let me draw a cross-sectional view. That's a circle. I know it's kind of flattened. So the inner one has charge per unit length minus lambda. The other one has plus lambda. And I want to calculate V. Somewhere in between these cylinders. What's the electric field inside the small cylinder?
Zero, right?
Yeah, there's no charge inside, right? If this is an isolated system, and we use Gauss's law, I have no charge inside. I know the electric field is zero. What about outside?
Negative?
Their charge distribution is opposite. Should it be zero outside?
It's zero outside. These are equal but opposite charges, right? Same thing as if I had two plates. The field, you have a non-zero field here, but outside you have zero field. Prove that to yourself. Just draw the field lines. So the electric field here is not zero. And it's essentially electric field due to this guy. It's basically the electric field due to a line of charge. And we derived the electric field due to a line of charge. The electric field due to a line of charge is this. Now it's negative because the electric field lines are directed radially inward. Sorry, the green doesn't show up very well. Okay, the electric field is directed radially inward, so it's minus 2k lambda over r hat. If this was if the charges were switched, the signs of the charges were switched, then this would be a positive. But we did the electric field due to a line charge. I don't want to use Gauss's law again to derive it. Okay, just in the interest of time. And if you don't remember, just go back to chapter 24. There's an example in your book. And I did this example anyway for the line charge. And so my goal is I want to integrate the electric field between somewhere in here. I want to calculate this to allow me to find the field inside. So I actually have couple of choices. So I'm going to integrate between A and B. Of course, B I'm going to call point R, because I want to find the electric field somewhere over here. I'm sorry, the electric potential somewhere over there. Okay. No, this problem I made is kind of ambiguous. I need to know the electric potential somewhere. How would I set this up? Well, if I wanted to set this up practically, if I had two long cylinders, of course they wouldn't be infinitely long, but to an approximation, this would still be valid. If I wanted to set this up, I would have two cylindrical conductors, and I'd hook up a battery to them. That's all I would have to do is hook up to a battery. So in general, I actually know this V and that V. I know them both because I'm using a battery, especially if I reference one of the terminals to of the battery to some voltage like ground. I know both of these potentials. Okay, but let's just integrate from the surface, the outer one, B. Let's pretend we know what that is. We'll just call it V sub B, okay? But in general, in a problem like this one, because this system consists of two conductors, I actually know the value of V for the two conductors because I set this up with a battery. That's it. Questions on that? Okay. So I want to reference it to B. I can reference it to A too if I wanted to. Okay, so I'm going to integrate.
Just as a quick question, that B is the radius B, right?
That's the radius B, yeah.
Okay.
Yeah. I can make it the radius A also, but that's either way is fine. Because like I said, normally with the two conductors, I know both the values. Okay, so it's going to be minus 2k lambda over r. And when I do this integration, actually when I do the dot product, I always choose my dr to point in the positive r hat direction. I mean the r hat component to point in the positive r hat direction, and then I let my limits of integration tell me whether I'm going outward, away from the conductor, or towards the conductor. If I start messing around with choosing a negative r hat, then the dr becomes complicated. I don't want to deal with that. Okay. That's not hard to integrate, right? Doesn't this give you a natural log? And so V sub r I'm done. I have V as a function of r. That's not too bad. This is a typical sample problem in a chapter. And you might see this example in chapters 25 and in 26.
And we're just calling V sub B a known value.
Yeah, it's some number.
Because we could put a battery on it.
Yeah. This could be 0. I mean, you can set it up so that this is the ground and this is not. I mean, this is whatever the battery voltage is, or I can swap them. Actually, this would have to be, since this is negative, this would be the ground, and this would be the high voltage. Make sense?
Yeah.
Okay. Well, if I know V sub B and V sub A, that will allow me to calculate lambda. Because if I know V sub B and V sub A, I can do the following. Let's see. That's going to give me and then that allows me to calculate lambda. So if I wanted to figure out what lambda was, I would do that. Now, in the next chapter, we define something called the charge per unit per delta V. Okay, the charge per delta V. It's called capacitance. And so basically what it is, this is a device that can store energy. And we describe it by calculating the amount of charge per delta V. Well, this has an infinite amount of charge because they're infinitely long. So for this particular one, we would calculate the charge per unit length divided by delta V. So we find the delta V between the two conductors, right? And we take lambda and we divide it by delta V, which delta V is this expression. So if we calculated lambda over delta V, we would get this. And this is defined as a positive quantity, so you always take the absolute value of this thing. And we'll talk about it soon. This is called capacitance. So I just did one of the problems in the next chapter. Okay. So since I did this problem in the next chapter, I will allude to it when we get to it, but I'm not going to go through it again since I just did it. Okay. And this is, in fact, this is called the capacitance. In this particular case, it's the capacitance per unit length. I can't call it the capacitance because this thing could store an infinite amount of charge. Okay, I can only talk about the capacitance per unit length because this is infinitely long. So it's basically charge per delta V, or charge per unit length per delta V. It's an important quantity because it's related to how much energy the system can store. Okay, and so I basically just did something from the next chapter. Okay, I want to spend a little bit of time, and I almost never have enough time to go through all the examples here, a little bit of time talking about applications involving the electric potential. I almost never have I never have time doing the parallel plate energy analyzer, although it's very easy, it's just kinematics. And there's examples in the book. But I want to say a few things. Now, let's look at electrical potential of conductors. What do we say about the electric field inside a conductor? What do we say about that? You got to remember this for the exam.
Inside the conductor, it is 0.
Yeah, the electric field in a conductor is 0. We also know that the electric field can be written as the gradient of the electric potential. Or if you don't like that, we'll live in a one-dimensional world. What does that mean then? What does it have to say about the electric potential? What does it say about delta V? if E is 0?
Also 0.
Delta V is 0. If delta V is 0, what does that mean then?
It means the electric potential is constant throughout the conductor.
Yes, that's what I was looking for. So throughout the conductor, the electric potential has the same value. And in fact, the surface of a conductor is an equal potential. And again, the reason why is the electric field points perpendicular to the surface of the conductor. So there is no gradient along the surface of the conductor. So the surface of the conductor is equal potential. In fact, the whole conductor is an equal potential. That's important to remember. Here is, and I'm going to blow up this picture. Suppose we have a conducting sphere. The electric potential for a conducting sphere is plotted in this figure. Outside the sphere, if it's charged, is kq over r, where r so the electric potential drops as 1 over r, just like that for a point charge. Once you get to the surface of the conductor, the electric potential is kq over big R. And since the inside is at equal potential, then it stays at kq over big R. That's the electric potential. It's continuous at the surface. Okay? But the electric field is not. Now, if you look at a spherical non-conducting surface, or actually non-spherical, let me rephrase that. If you look at a non-spherical conducting surface, that picture shows the equal potentials for that system. Notice where the equal potentials are most, are sharpest. That's where the field lines are bunched together. So the electric field is greatest around the sharper curve, since the equal potential surfaces are sharper in those regions. Now, I don't have time. I was going to do an example where I actually have a weird shape charge distribution, and I calculated the electric potential on the whole thing has to be constant. But I calculated electric field on both sides. I approximated the electric field and charge density on either side of that surface, and you can easily show that the sphere of radius R2 has a much bigger field. Okay, and if you're interested, you can read through that example. I don't have time right now to go through it. You can always ask me questions about it, like on Thursday during office hours. Okay. What about the electric field in the cavity of a conductor? So there's a conductor with a hole in it. It has some thickness. The conductor is an equal potential surface. The integral has to be 0 along any path between points A and B. And since the inside the conductor is empty, there's no charge inside the conductor, then even in the cavity, the electric potential has to be constant, because the field's 0 inside. Now, if you have a conductor, conductors really can't You can't put an infinite amount of charge in a conductor. Okay, because what will happen is the field near the surface of the conductor will be so high that it will strip electrons from nearby air molecules, causing the air molecules then to start conducting. The air will start to conduct. We say that the air breaks down, or the medium breaks down. For air, this breakdown electric field is about 70,000 volts per inch. And that's what you see when you play around with a Van de Graaff. So the breakdown voltage for air is about 3 million volts per meter, or 70,000 volts per inch. So when you see a Van de Graaff and you see it makes those sparks, even when I did the demonstrations in lecture, it was producing probably around 70,000 volts per inch. That number varies. That's an approximate number, depending on how much moisture is in the air. The more moisture in the air, the less of a voltage required, or the smaller electric field is required to get the air to break down. All materials have a breakdown voltage. Some gases have a very high breakdown voltage, some do not.
So when I was, I'm sorry to interrupt, while I was doing my lab 2 and I was getting static, visible static discharge, was that field in the range of this?
How big was the arc?
I was getting like at least a quarter of an inch at some points.
Yeah, we're talking maybe at least 10,000 volts.
Okay.
But there's not a lot of charge there to cause any damage. Right. Yeah, so like if you're from the Midwest, if you you don't experience it here, but in Midwest, a lot of folks wear those nice wool sweaters because it's cold outside. And if you take that sweater off, especially if you're near a fluorescent bulb, you can see that fluorescent bulb flickering because you're producing a lot of static. Or you're walking on the carpet and you touch someone and you zap them. And you give them a pretty good 10,000 volt zap. They'll feel it, but it's not a lot of charge, so it doesn't cause damage. I mean, when I got zapped, I did a demo with the Van de Graaff the other day. I got zapped with it. That was probably about 50,000 volts. But still not a lot of charge. You feel it, but it's not dangerous. I mean, unless you have a heart problem. So here's an example. This is on YouTube, by the way. You can find this on YouTube. So the discharge is called a corona discharge. The breakdown that you see is called a corona discharge. So here's an example at a power plant. Take a look at the size of the people and the size of the arc. Okay. You saw how big that arc was compared to the people? You can imagine how dangerous that is. Now, if you look at chapter 26 of your book, it'll actually list the breakdown voltage of various materials. It's in volts per meter because, actually not the breakdown voltage, the breakdown field for various materials. Okay. Even insulators, things you think are insulators, if you put a large enough potential across them, they'll break down. All right. The last thing I want to do, before I do my special example, is to discuss this problem. And really what I want to do is set it up. I have the entire solution in your notes. So you can look at the solution. But once you set it up, the rest is basic algebra. So let's say I have two conducting spheres. And I'm going to put them far apart, and I'll tell you why in a little bit. Let me draw the picture. So here's this first sphere. We'll call, and it's at some potential V1. It has radius R1. And here's my second sphere. Radius R2. potential are V2. And what I'm going to do, oops, what happened? I'm going to connect the two conductors together with this thin wire. Oh, now, first of all, why do I have them far apart? Why do you think I have to have?
So that we can say the electric potential has no impact because the distance is so great between the two spheres.
Yeah, because if you're right, if they're close to each other, what are they going to do? They're going to cause the charge on each other's spheres to rearrange, right? Because conductors have free electrons on them. If you put them close together, you're going to have the charge redistribute itself. And then the problem becomes really difficult. So I'm putting them far enough apart so that the charge distributions on either sphere don't influence each other. Now, I put a conductor between these points. This potential is at this sphere is at a different potential from this sphere. What's going to happen? What's going to happen when I connect them together with a wire?
I would say those electrons that we didn't want to rearrange themselves are going to rearrange themselves.
Yeah, it's like I have a battery, right? It's as if I have a wire connected to a battery. So charge is going to flow along the wire. Until when? How long is charge going to flow along the wire? What condition must be satisfied for the charge to stop flowing? I mean, this is different from a battery, right? Because a battery maintains the potential difference between its two terminals, and so it's going to keep charge flowing along a wire. But this is not going to maintain the potential difference between its two terminals, because if charge flows this way, this V goes down. Right? Because V is K, Q, or R, right? Or a sphere. This will change. This stays constant. So charge will flow. Let's pretend it goes that way. This will decrease until when?
Until it's zero?
Not until it's zero. When will electrons stop flowing? Well, I guess I should say, what's zero?
Until there's no more electrons?
Not necessarily.
Until the delta V is zero.
Not V is zero, but...
The delta V.
Yeah, that's right. Until the delta V is zero. All right? Because when delta V is zero, you can't get... There's no field in here, right? So charge will flow until the electric potential on both spheres is the same. I mean, once you connect them together, they become a single conductor. Once you put that wire between them, this becomes one big conductor of a weird shape. The charge will stop flowing when this V and this V are the same. So this thing initially had Q1 on it, Q1 initial, and this had Q2 initial. When charge stops flowing, this will have some other final charge, Q1 final, and this will have a final charge, Q2 final. So charge will stop flowing until both V's are the same. So that means then that K Q1 final over R1 has to be equal to K Q2 final over R2. Can I figure them out? Can I figure Q1 final out and Q2 final out? Furthermore, can I find V final for both spheres? I could, but I need one more equation. Where would I get my other equation? Well, initially, total initial charge was Q1 initial plus Q2 initial. Okay. How much charge will I have left afterwards?
The same.
The same. The charge can't go anywhere. And so there's my second equation. By the way, if I know V1 and R1, I can calculate Q initial. If I know V2 and R2, I can get Q2 initial. And so then I have two equations, two unknowns, I can solve them. Make sure you understand conceptually what this means. Okay, because as we talk about circuits and capacitors in the next chapter, this is important to understand. And so now it's just a simple algebra problem. You guys can all do that. Once you have these equations, this is a simple problem. You guys can all solve that. Now, if they're both at the same potential, if this has a smaller sphere, if this is a smaller sphere, this will probably have a larger electric field than that one. So in my notes, I go through and calculate, I go through every possibility for this problem. So I have basically all the solutions, all the final. You don't have to remember the solutions because the math is easy. Okay. The one thing to realize is, whatever this sphere loses is going to be equal to whatever this one gains. Because charge is conserved. So if this loses 1 coulomb, that'll gain 1 coulomb. Charge has to be conserved. Okay? So you can write these equations differently because Q initial plus delta Q is Q final. Q2 initial plus delta Q is Q2 final. And I go through that process in the notes, so you can take a look at it. You can read through it. Okay? And I actually go through and calculate the electric fields too. So go through that. So if you want a problem to solve with an answer in front of you, go through and solve that problem. That's really good practice for the exam. Okay. So I'm going to do one more special example. I'm really done with, essentially done with chapter 25. I'm just going to do one special example. Hopefully it'll only take me 15 minutes. The parallel plane analyzer is an interesting problem. It's just kinematics. We actually have done the parallel plane analyzer problem in chapter 23, but we wrote everything in terms of electric field instead of V's. Let me do one special problem. In fact, it's really discussed in chapter 25. And normally I talk about this when I do the properties of charge lab. Suppose I have a dipole. Okay, suppose I have a dipole. And if you remember, that dipole moment is Q times L, where L goes from the negative charge to the positive charge. And let's say the dipole is in a uniform electric field. Tell me, what's the force on that dipole? What do I do if I want to figure out that answer?
We use force is equal to Q times the field.
Yeah, well, I want to draw a free body diagram, right? So I can write equations down, but isn't it true that the force on this object is this way? And the force on this guy is this way? The E's are the same, the Q's are the same, the arrows point in opposite directions, so the sum of the forces equals?
Zero.
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 Yeah, so the force on a dipole in uniform field is zero. Let me ask a harder question. Let's say the dipole is oriented in the x direction. The electric field is oriented in the x direction. What's the force on the dipole in a non-uniform field? What is it in a non-uniform field? Well, again, from my free body diagram, let's say this location is x and this location is x plus delta x. So this force is the force at x, and this is the force at x plus delta x. So that if we sum the forces, we're going to get Q at E plus x plus delta x. I'm not going to put arrows over it. Let's be a little more precise. Whatever delta x is. Delta x is usually very small. It's a small distance. Let me multiply numerator and denominator by delta x. Oh, what's delta x times q? Dipole moment. So I have a q. Oh, I forgot the q here. Sorry. So q delta x is the dipole moment, which is along the x direction, and I get E at x plus delta x. And I really don't need the arrowhead over it because we're only talking about everything in the x direction. And what if I take the limit as delta x goes to 0? What is this thing? If I take the limit as delta x goes to 0, what is this thing? First thing you learn in Calc 1.
Indeterminate form, 0 over 0?
Yeah, but this is called a difference quotient.
Oh, yeah.
Isn't that a derivative?
It is.
Okay, so this is p sub x dE over dx. And I'm running as a partial because if you do this in general, you have to write partials. Okay, but maybe I shouldn't do that for now. I'll just do this. Now it gets much more complicated if P is oriented in some arbitrary direction in 3D and the electric field has 3 components. So it becomes much more complicated. You can derive the equation, but it takes a lot more work. In fact, there's another way to do this. Okay, there's another way for me to do this. I can look at this expression. Let's get rid of this delta x stuff. Let me rewrite this expression. Let me forget the arrowheads. Okay, and then there's a q on the outside. If delta x is small, I can expand this term using a Taylor series. And this term disappear. And I'm left with the E prime is the derivative of E respect to x. But again, I mean, this is the best way to do it, to derive it. Because when you want to generalize it to 3 dimensions, you have to expand, you have to do a Taylor series expansion in 3 dimensions, which is, I think you learned that in Calc 3, if I remember correctly. Okay, and then you can derive the general equation, which is kind of nasty. Suppose I have, let's do another problem. Suppose I have a dipole at some angle, like this. And it's in a uniform field. Let's make life easy for ourselves. Okay? This vector is L. And let's let the electric field be uniform and point to the right. What's going to happen to that dipole?
Is it going to start rotating?
It's going to rotate. So can we calculate the torque? Right, we can calculate the torque on this thing because torque is R cross F. So let's choose that point for calculating the torques. Here's one vector. Here's another vector for our R. So we're going to have Q times L over we're going to have L over 2 cross QE. This vector points in the opposite direction, minus L over 2 cross minus Q times E. The minus and the minus cancel, and I get Q times L cross E, which is P cross E. So the torque on a dipole in a uniform field is just P cross E. We're not doing. Don't worry about the torque on a dipole in a non-uniform field. That's nasty. Okay. We're not going to do that. Well, if this thing is rotating in a conservative field, then you're going to have energy stored. The work done by a torque is going to be the integral of the torque d theta. This is chapter 10 of your textbook. And so this is going to be, well, if we write that as a magnitude, it's going to be like this, sorry. It's going to be P times E sine of theta d theta. You integrate between two angles, theta initial and theta final. What is the integral of sine minus the cosine? And so the work done by the field in rotating that thing is minus the energy stored. So delta U is PE cosine theta final minus cosine theta initial. And so it's going to be U final minus U initial. The biggest angle is 90 degrees you can get. So I'm going to make cosine, I'm going to make theta final 90 degrees. And I'm going to define, since cosine of 90 is 0, I'm going to say u final is 0. I have a minus sign error. Hold on a second. Oh, I made a minus sign error. I did make a minus sign error. What happens to theta when I put this in the field?
That's going to want to rotate clockwise, so theta will get smaller.
So my d theta is going to be negative. Since d theta is less than 0, I got to put a minus sign here. So I forgot another minus sign. I was wondering what the heck was wrong. So there is a minus sign here. And so u initial then is minus p e cosine theta initial, or we can write in general u is minus p e cosine of theta, which is the initial angle. So the energy stored is minus p dot e. And you'll see a problem involving that in the homework. Okay. So just some interesting stuff regarding dipoles. Where does this dipole thing come from? I mean, where did it come up? It is used in solving problems. So a lot of problems are very difficult to solve, and so we make approximations to make problem solving easier. So we'll make approximations and we'll realize, oh, these extra terms are going to be so small I can ignore them. If you do this problem, and by the way, there's a document on Canvas with this problem that's completely solved. Professor Shakel made the document, and I have to thank her for that because it's really well written. You just look at the following. Suppose I have a charge here and a charge here, and I want to calculate the potential at this point. I want to calculate potential at this point due to these two. And I want R1 and R2 to be much, much bigger than L. So you set up the equation for the potential due to 2-point charges. And then what you do is you do an expansion to the function, and that's where you see the dipole moment come in. And you just keep the term with a Q and the L in it. That's where the dipole comes in, because all the other terms are going to be useless because they're going to be too small. That first term will be enough to give you information you need to solve the problem. If you have 4 charges, like this, and you do the same thing where P is real far away, then the dipole term will disappear. The next term in the expansion will be non-zero. That's called a quadrupole term. And these terms in the expansion, we just keep the first term that's non-zero, so that we can actually get some feeling for the behavior of the system. Because just keeping that first term, assuming all the other terms are going to be very small, will allow us to figure out a lot about the system. We don't have to get an exact value. I spent a lot of time in graduate school physics doing problems where you just do expansions to functions, because that'll make the problems doable. So I wanted to say a little bit about dipoles. Please read the document on Canvas on dipoles, okay? To get a better idea where all these these P's come in. All right, so I'm gonna. I got a few more minutes. Let me introduce to you the next chapter. A little bit behind, but that's okay. I'm pretty confident we have no problem catching up. So the next unit we're going to focus on charges moving in conductors. Although chapter 26, we're really not going to be looking at charges moving in conductors. It's really chapter 27 and 28. So our unit 3 is really more on circuits. We're going to learn about capacitance, and capacitance is something that's very important when you're working with circuits, but it's actually important elsewhere. All right, but our focus will be more on circuits. If you take a junior level course on this topic, you'll see a broader description of what capacitance means. Okay. And we'll talk about some examples and some applications. But we won't talk about the applications of capacitance in circuits until the end of chapter 28. And I think capacitance is not, at least at the introductory level, it really shouldn't be that hard a subject. It's just different, and sometimes students struggle with it. But I think the material in this unit should be less stressful than Unit 2. So Unit 3 is chapters 26, 27, and 28. I think this unit should be less stressful, but it's easy to make silly errors as a result of misunderstanding a concept. So let me begin by I just want to introduce the idea of capacitance today. Suppose we have two isolated conductors, or a single isolated conductor. Okay. One can do an experiment, and if I was trying to do the demo here, it's very hard to do the demo. You can do an experiment that the total charge on a single isolated conductor depends on the size and shape of the conductor and the electrical potential. Even if you have a pair of conductors, the amount of charge you can put on the pair of conductors will depend on your delta V between the two conductors and the size and the shape of the conductors. And you can show that experimentally. So what we're going to do is we're going to define a quantity that relates the electric potential to the amount of charge and energy stored by electric field. We're mainly going to focus on pairs of conductor. What we're going to define is something called a capacitance. When you talk about the capacitance of a pair of conductors and you say, well, it tells you about how much charge you can store in a conductor, on a conducting system, I don't like that definition, because when you connect a battery to two conductors, one conductor is going to have charge plus Q, the other conductor is going to have charge minus Q, the total charge is 0, but there is energy stored in the field. So we're going to define the capacitance as the ratio of the magnitude of the charge on one of the conductors one of two conductors, or a single conductor, divided by the electrical potential difference. Our focus is going to be on working with pairs of oppositely charged conductors. These devices are called capacitors. They store energy and they have a lot of practical applications in real life. They have applications in circuits. They're on your keyboard. Each button on your keyboard is a capacitor. Okay. The random access memory, for example, on your computer involves using capacitors. There's a lot of applications of capacitors. It's all electronics. So what happens when a battery is connected to a parallel plate capacitor? So you have a battery, and I'm not going to draw the schematic diagram of the battery. So let's say I have a battery. And here's two plates, plate 1 and plate 2. I make these connections. What happens? Charge will flow to the plate until the potential here is equal to the potential here. Charge will move here until this potential equals that potential. When a positive charge gets here, or in other words, when an electron goes into the battery, then this is going to see a positive charge here. It's going to draw up an electron. As this becomes more positive, this becomes more negative. Of course, that happens very fast. This is why the charge sharing problem is important, because when I make this connection, charge will flow here until the potential on this plate equals the potential of the battery. Same thing with the other side. And this thing is called a capacitor. This is called a parallel plate capacitor. It's a device that stores energy. And people will say it's a device that stores charge. And again, I don't like that, because what happens is when this thing is fully charged, this has plus Q on it, this has minus Q. The sum of those two is 0. In total, there's no charge, but there's energy stored. So you can always think of the capacitor as a device that stores energy. And I'll do some demonstrations over the next couple of lectures that show you that capacitors store energy. I can take a capacitor, store energy in it, and then make a light bulb go on with it. Or I can make a flash cube, a flash bulb burn brightly. I will do those demos. Okay? Although they are more impressive in person. All right, so I'm going to stop here, and then I'm going to continue this discussion next time. Okay, so I just want to introduce to you what a capacitor is. By the way, before I finish, again, our focus on capacitance is with two conductors. You can define capacitance for a single conductor, and I'm going to mention that. But you can define capacitance for multiple conductors. And again, in a more advanced course like in physics and engineering, you would see that. Okay. All right, so I'm going to stop here. And I will see you on Wednesday. Please try to get as much of the chapter 25 homework problems done as you can.
Thank you, Professor.
Sure, no problem.
Yes, thank you.